Hello class, this is Tim Tomlanovich. This is Water Technology and this was Learning Plan 3. All right, Water Technology Learning Plan 3. So let me get my cursor down here. Okay, let's talk about flowing pipes under pressure. So there's something called a hydraulic grade line, HGL, hydraulic grade line. The HGL is a graph of pressure head along the pipe plotted above the center line. The HGL always slopes downward in the direction of flow unless additional energy is added by a pump. And the vertical drop in the HGL hydraulic grade line between two sections separated by the distance L is the head loss HL. So if you look here, they call slope, the slope of a line is change in height over length, right? That's a typical equation for a slope of a line. So if you look at this, head loss divided by loss will give me my slope. So let's look at these pictures right here. So I have hydrostatic pressure here, if you look right there, okay? And the valves are closed. So when the valves are closed, there's no flow. So as you can see, the height of the water comes to equilibrium. It'll stay there, okay? Now if I come down to this picture, the valve is now open. As you can see, the water is going to start flowing this way. And as water flows, water particles create friction upon themselves and along the sides of the walls. So as further we get away from the source, the piezometric pressure actually will decrease in the direction of flow. So that's how we measure flow, hydraulic grade line. Okay, so if we actually put a piezometer in there, you can actually measure that. We can actually calculate the hydraulic grade line. So we use this concept in soil mechanics, groundwater flow. So what we do is we'll actually put, like, especially in dams downstream of downslope, downstream of the earth embankment, we'll put a well. We'll put wells in a linear line, and what we do is we want to measure. We'll actually want to measure the height of the water and to determine which way the hydraulic grade line is going. We want it to go down. We don't want it to go up, because if it goes up, then we start getting piping in dams. So this concept is typically, we use this a lot in soil mechanics to bring it back to a different subject. So this understanding the hydraulic grade line, S equals head loss divided by length. Okay? So now understanding the concept of hydraulic grade line, we can talk about flow in pipes under pressure, and the Hazen-Williams equation. Q, okay, Q is flow rate, so be careful, is in cubic meters per second or in gallons per minute. Okay, depending, so gallons per minute is the English units. And cubic meters is the metric. So C is called a pipe roughness coefficient. Okay, that's that guy right there. Pipe roughness coefficient, and we'll talk about that in the next slide. 0.28 is this a factor based when they derive this equation. So that's a constant value. This 0.28 is a constant value. So my flow rate is 0.28 times my roughness coefficient, which is a unitless number, times the diameter of my pipe raised up to the 2.63. So diameter is in, metric is in meters or inches in English. So okay, that's a little bit different than what we're used to. Times S, slope of HGL. Slope of the hydraulic grade line is unitless. Oops. Okay, because if we look, we go head loss divided by length, so that's in meters per meters, feet per feet, inches per inch. It doesn't matter. It's a unitless number because we're taking, make sure the units are consistent, okay? Make sure the units are consistent. Okay. So here's that coefficient. So in your textbook, when you read the textbook, smooth plastic pipe has a roughness coefficient of 150 and concrete has a roughness coefficient of 130. So typically when you think about when you're doing pipes under pressure, as they get older, they get rougher, so they resist more flow because there's more friction on the interior walls of those pipes, especially cast iron, concrete, sanitary sewer and all that. So this is a very kind of important concept. So basically, the smoother the pipe, the more flow we can get. So newer pipes are smooth and allow more flow, and we typically have a coefficient greater than 100. And older pipes have more resistance to flow, which is less to 100. So those aren't really published values; those are research values. So it's just something to keep in mind when you say you're designing flow, in a water line, okay, under pressure, okay. So basically, over time, that pipe in 50 years, that pipe isn't new anymore, especially clay, vitrified pipe, concrete. It'll get rougher and rougher over time, so that pressure is going to decrease over time. So that's why there's the big move on using plastic, because it stays fairly smooth and that our flow doesn't change much. All right, so it's quick and easy, however less accurate. Estimations of flow can be made using the Hazen-Williams nomographs. So we have a nomograph, or we can use this equation. A separate nomograph is required for each value of C. Okay, so the one in your book on page 34 uses a coefficient value of 100. Okay, when you look at figure 2.215 on page 34, they use a coefficient value of 100. Okay, so basically what that's telling you, if I was using smooth plastic pipe, a new graph would have to be created for pipe and concrete, separate pipes, to use a nomograph for a really quick estimate of our flow rate in pipes using Hazen-Williams equation. Okay, so with that, let's get on to the examples. So we'll do 212, 213, and 214 of your book. And I have the homework listed right in Blackboard there, right underneath the learning plan. And then if you have any questions, remember I'm available from 11:30 to 2:30 on Tuesdays via WebEx if you have questions on any of this material. Okay, so example 212. I am on page 34. I'll read the problem out loud. A 12-inch diameter pipe carries water with a head loss of 10 feet per 1,000 feet of pipeline. Determine the flow rate in the pipe using the nomograph in figure 215. Check the solution using equation 2.9. Okay, so we're going to do both. All right, so let's write down our knowns. So we have a 12-inch diameter. D equals 12 inches. And we have a head loss of 10 feet. Slope equals 10 feet per 1,000 feet. So our slope is, our hydraulic grade line slope, 10 divided by 1,000 is 0.01. Okay. Per 1,000 feet. Determine the flow rate. So it's asking us to find Q. Okay. So I'm going to write the equation down. We'll do the equation first in the nomograph. So Q, it's asking us Q equals 0.28 times C. Oops, why did I put 10 there? I have no idea. Times C times D raised to the 2.63 times your hydraulic grade line slope raised to 0.54. Okay. All right, so Q equals 0.28 times, so we're going to use 100 because that's what the nomograph is, times D. So now does D need to be in inches? Yes, meters or inches. So times 12 raised to the 2.63 times our slope is 0.01 raised to the 0.54. So Q equals, so just be careful units, so 0.28 times 100 times 12, the caret key on your calculator, so raised to the 2.63 times 0. Oops, screwed up. 0.28 times 100 times 12 raised to the 2.63 times 0.01 raised to the 0.54. I get 1604, 1605. Q equals 1605 GPM, gallons per minute. Okay, now let's go to the chart. So we know this is C, so we know we have this variable, we have a diameter, and we have a slope. Okay, so basically you can only have one unknown variable to use this chart. Okay, so with that, let's figure this out. So basically what you do is, let's go to slope. So we have 0.01, which is right there. Okay, this kind of shows you, but we'll use it with the other examples too. D, so look at which side you're on here. So you see here, one side is metric, or one side is English and one side is metric. So just be careful you're looking at the right units. D is 12 inches. So literally what you do is you connect those two dots like they're showing here, and you hit it. So this is 1,000. That's 2,000, 1,200, 1,400, 1,600, 1,800. So see, it's just a little over 1,600 gallons per minute. So using the chart. Okay, so that is example 212. All right, 213. That is 213. An 8-inch diameter pipe carries a flow of 1 cubic feet per second. Compute the pressure drop per mile of pipeline in 10 PS, or in PSI. So we have D equals 8 inches. Okay. Flow Q equals 1 cubic foot per second. Compute the pressure drop per mile of pipeline. So we're trying to find pressure drop. So that S equals head loss over length. So this term right here is the pressure drop, head loss, right? Okay. So we know L is per 1 mile, and we know that is how many feet per mile? 5,280 feet. So we need to calculate that. Okay. All right. So we could rearrange this equation to find S, couldn't we? Doing algebra. We know Q. We have to get it. Q needs to be in gallons per minute. We know C. We know D. So we could do algebra, rearrange this equation to find S. Okay, so I'm going to use the chart. All right, but what I recommend is you practice your algebra so you know how to solve for each of these variables. Isolate these slope. Okay, and then once you know slope is HL over L, then you can solve for HL. Okay, so it's important that you practice your algebra. If you're struggling with that, you need to come see me and I'll help you with it, okay? So in the meantime, okay, so first, we're going to use a nomograph. So we got to get Q into metric. So write down what you know, write down the equations, and then start solving the problem. So we need to get Q in gallons per minute. So Q equals 1 cubic feet per second. All right, cubic feet, so we know there is 7.48 gallons per cubic feet. So cubic feet is in the numerator on this side. It has to be in the denominator when I'm multiplying it on that side. That cancels out. Now we're in gallons. So remember, we need gallons per minute. Okay? Times 60 seconds per 1 minute. Again, we have seconds in the denominator here. We need seconds in the numerator there to get, now we're in gallons per minute. And we get, when I multiply that out, 450 GPM, gallons per minute. All right, so now we need to solve S. So we have D, we have Q. So basically what we do here, I'll use my red here. So we know a Q. Q flow rate gallons per minute is 450. So that's 400, 500. So we start there. We know our diameter is 8 inches. Say pipe 8 inches. Units, just look at your units here. As you look here, it'll tell you what units you need to be in. So if you're not in those units, you better do some conversion. So we know we have 8 inches. Okay, now what we need to do is, I'm going to pretend I have a straight line here. Oh, wait. Oh, look at this. I can connect these points. That is awesome, isn't it? Okay. So we know from the nomograph, S equals, so that's 0.0070. So that's 0.0060. I'm going to estimate 0.00, so somewhere in between, right? About halfway between 0.0060 and 0.70. Okay, so now, this was step 1, this was step 2, this is step 3 from the nomograph. Now step 4, we know S equals head loss over length. Okay, so we know slope over hydraulic grade line times my length equals head loss, and that equals, we know we have 0, our hydraulic grade line slope is 0.65, and we know our length is 5,280 feet, and that equals 0.0065 times 5280, and I get 34.32 feet. So about 34 feet of head loss. Per mile of pipe head loss. So let's bring that back to P equals 0.43 times H. Okay. So if H, so H is head, right? And this pressure. So if I take that, okay, that needs to be in feet, right? 34 times 0.43. So we're losing 15 psi of pressure per mile of pipeline. Okay, so that's why this Hazing-Williams, so we can calculate how much pressure we're losing in per mile of that 8-inch diameter pipe based on this coefficient of 100. Okay, so it's something to go back to it. So if your house is a mile away, basically we're losing 15 psi. So that's part of waterline design. Okay, based on that. So could you, so this could be a surveying thing, right? Basically measuring grade lines, measuring the invert of water lines from point A to point B, and then they can run a pressure test on it and they can actually calculate all this. So this is all mathematics and surveying. Okay, so that was problem 2.13. So our final answer, don't forget the box in your final answer, is 34 feet. Okay. Oh, it does act. I'm sorry, I didn't answer the question. Compute the pressure drop per mile of pipeline in psi. So that's 34 feet. So P equals 0.43 times 43, and that equals 15. So I did actually have to do that. So that's 15 psi. Apologize for that. I didn't answer the question. So the final answer is 15 psi. Because the problem is compute the pressure drop per mile of pipeline in psi. So first, I needed to calculate my head loss, and then I went back into this equation to find my psi. So 15 psi per mile. So from 2 miles away, I'm losing 30 psi. Okay. All right. So then, again, we can rearrange that equation. I want you to figure out how to do that, because we can do it mathematically too. 2.14. What minimum pipe diameter is required to carry a flow of 30 liters per second? So Q equals 30 liters per second. Okay, so if I look here in the metric, flow rate equals, if I look here, is liters per second. Okay, so if they give you cubic meters per second, you just got to do a unit conversion. There's 1,000 liters per 1 cubic meter. Okay, we may have to do some conversion. To carry a flow of 30 without causing pressure drop more than 10 kPa per kilometer of pipeline. Okay. All right. So without causing the pressure, what is the minimum pipe diameter? So we're looking for D. Whoops. We're looking for D. Okay. That's what we're looking for. All right. So, and pressure drop. Okay. Pressure drop. Less than, it says, I'm sorry here, causing a pressure no more than 10 kPa per kilometer. 10 kPa per kilometer. So my L equals 1 kilometer, or 1,000 meters, right? Because pressure drop equals H head loss divided by L. So again, we're looking for that. That has to be in meters, correct? So knowing, so you just kind of, my thought process here, writing down what I know. Okay, I'm knowing L is related to this slope, L, HL over L. Okay, and now I can start solving this thing. All right, so we know P equals 9.8 times H, and that'll be in kPa, remember? So if I take P divided by 9.8, well, that'll give me my H. Okay, so with that, I put 10 kPa, right, because that's my pressure drop that I do not want to exceed, divided by 9.8, and that'll give me my HL term, right? My H equals HL. So 10 divided by 9.8, so 1.02 meters. Okay, so now I can calculate my slope, the S term. So 1.02 meters divided by 1,000 meters, 1.02 divided by 1,000. So I get a slope of 0.00102. So that's one term. All right. So see how that worked? So, all right. So Q equals 30 liters per second, or times 1 cubic meter divided by 1,000 liters equals 0.030 cubic meters per second. Same thing. But when you look at this chart though, don't go to 0.03, you want it in liters per, it's these two values are equivalent. Okay, so all right, so we have our hydraulic grade line, our S term. Okay, we have our flow rate of 30 liters per second. So, and it's asking us, again, the question is asking us what? What is minimum pipe diameter is required to carry a flow of 30 liters per second without causing a pressure drop more than 10 kilometers per pipeline. Okay, so with that, let's go to our nomograph. So S, 0.00102, 0.001, okay, 10, so I'm going to say that's maybe right about there. I don't know, is that the halfway mark there? Somewhere in there, right? Okay, we know our Q is 30 liters per second, right there. So now, I got to connect these points. This is so cool, I got my laptop on this. Okay. So, my diameter is about, if I look here, about 300 millimeters. Okay. From the graph, D equals 300 millimeters, or 0.30 meters. So a diameter of 300 millimeters can carry a flow of 30 liters per second at a hydraulic grade line of 0.00102 without exceeding a pressure drop of 10 kPa per kilometer of pipeline. Okay? So that is the example. So what I want you to do is be able, one, for practice, be able to rearrange this equation to solve for D or S or C. Okay? Learn algebra again. Be able to calculate S, D, C. Okay? Separate those terms out using algebra. And then what I want you to do, so we use the equation here. I did not show you the equation here. What I want you to do is do the rearrange the equation to solve for S, right? Because then you can find HL. So rearrange that equation to solve this one. To see how, because that's a check based on the nomograph. And then I want you to rearrange the equation to solve for D on this one to see if you get that answer using a calculator. Okay, so, and then additional, do the problems that I recommend in Blackboard. Thank you and good luck. So let me, okay.